This is a capacitor. I've been thinking a lot about these guys lately. The capacitance of a capacitor, C, is equal to the charge on that capacitor divided by the voltage across the capacitor. Capacitors are two conductive interfaces that are not connected, instead separated by a non-conducting material called a dielectric. If you apply a voltage across the terminals, charges will start flowing into the capacitor. So while capacitors can be charged, they can also be discharged, but only for a short period of time. And since they can store charge, they can also be thought of as energy storing devices.
I'm here today to talk about the completion of a big project, but I'm also going to show you what allowed me to complete that project safely and with great confidence that this project would work.
This is supposed to be a wrist-mounted grappling hook, but it's actually just a stepping stone to something greater. I call it a milestone project, one that allows me to learn how a certain technology ticks so I can best apply it to a larger goal. You've seen me create a wrist-mounted motorized rappelling device. That's another milestone project, allowing me to learn what is necessary to support a human being from a reasonably sized cable attached to the wrist and to automatically store that cable such that the device doesn't have external hooks or attachments to the environment, rather becoming an extension of the human body. As a milestone project, this wrist-mounted grappling hook is essentially a miniaturized and weaker version of what it will eventually become, and allows me to learn what it takes to have a limited number of electric motors perform mechanically complex functions. This allows an electrical signal to fire a projectile attached to a cable and then retract the cable to a position such that the projectile is ready to be fired again. A resettable system. The only problem is, this milestone project has been going on for way too long. Ta-da! So it doesn't work. Okay. But in this two-part video, I'm going to show its completion. Today, I'm putting focus on some radical hardware developments that allow me to have a better handle on the mechanical issues that plague this device. What I'm going to save for later is a discussion about how this technology will one day integrate with the rappelling device and my ideas for more advanced projectiles. The future and purpose of this project will be revealed. Today is all about solving engineering problems.
Well, okay, kiss, marry, kill. Phillips chamfers right angle edges. Let's get down to it.
And of course, we're going to delve into a little engineering education along the way. Let's start with the day I published my last video about my 8-legged robot, Charlotte. Whew. That took way too long.
I bet you feel pretty good about yourself now, right?
What?
You think just because I have radio control you can say I'm a complete robot?
Look, I can't give you all the attention all the time, all right?
So what's next?
Probably the cable shooter. I mean, that's the one thing that I started back in 2023 that was supposed to take like 2 months, and here we are entering 2026. It's unacceptable. You know what I mean? It's ridiculous.
Yeah, you are really falling behind.
Well, what am I supposed to do? It's like it's cursed. It's like the universe doesn't want me to finish it.
You have no one to blame but yourself. You built the damn thing.
Yeah, I know you're right. I know. Well, Charlotte, I guess this means we're going to open a new project file. We're going to start fresh.
Good for you. I'll be over here waiting for you to fulfill those pre-orders of me.
We're going to get this thing working like it should. I don't know what it's going to take, but we're going to do it together. This is the project that should have been paired with the rappelling hook to create something, I don't know, something amazing, something ultimate. The craftsmanship that's required seems to be out of my wheelhouse, but I'm determined to drag that craftsmanship back into my wheelhouse, kicking and screaming. I had a lot of problems to deal with. All my soldered wire connections would often break while moving the device's components around. I had a mess of wires generally. I couldn't get the device to work when I put a cover on it, and any cover I made was way too difficult to assemble. Anytime I would fix a mechanical problem, some of the electronics would break and vice versa. It seemed impossible to ensure that the extremely stiff spring that does the launching would be exactly fully compressed by the time the latch, which is driven by the same forward sliding mechanism, releases the projectile. The mechanical coupling and decoupling of the reel from the drive gear was often and unpredictably misaligned. Last but not least, I have noticed that across many of my projects, whether it be Charlotte, the web, this project, motor drivers have been inexplicably burning out. So I set myself to task with solving these problems with a heavy CAD redesign.
So this is what happens in CAD when you get a circle that's not a circle. So we're going to draw a circle on the circle. Well, it could be optimized. I mean, this won't be there anymore. And then this one Going to be lubed up so that we can see what it looks like when it's meshed together. Oh, you know what I got to do? I got to measure the angle. Measure between this one and this one. 6.6 degrees. Beautiful. And now what I'm looking for here is to make these one part, a 32 millimeters screw. Okay, we're going to make the head on this now. My caliper's broke, by the way. That's why you're seeing me slumming it with the measuring tape. I am going to need to cut these screws to 32 millimeters, and they're currently 40, but that's okay. Split this body here. I'll probably just replace most of it. Okay, now we're going to loft this one. Why? It's a circle. Oh, I guess it's not a circle. You know what? We need clean CAD. Thanks, guys. Thanks for being in this live. Appreciate it. Why is this so off-center? What is going on? Yeah, that's not centered at all. Brother, what is happening? This is so dumb. Why is this off-center? So those two faces are parallel at least. That's good. I feel like from here I can probably just make it work. But let me see if I can make things a little more circular first. Is this not circular? This isn't circular, is it? Is it? I got my PhD back in June. Well, I just went to graduation, but I defended my PhD back in June. And it was a lot of fun. Maybe one day I'll stream and we can react together to my defense. Wait, why is that still off-center? I swear that the whole thing was on center now. What? Wait, what is going on?
One solution that helps mitigate a bunch of the issues with this invention is the separation of the device into 3 separate modules, which can be connected using simple electrical connectors. These modules would be the mechanical module, the programmable electronics module, and the battery module. 3 different modules that'll be chained together independently. The mechanical module is the one that really needs the attention. It's the one that needs to work properly. It's not like this project has any super advanced or cutting-edge electronics. This way, if I need to work on the mechanical module, I can separate it from the other 2, so as not to damage them in case a tool slips or I make a sudden unexpected movement, which is often. There's a reason I'm not a surgeon.
I don't eat raspberries, Christopher. I eat apples, and I love grapefruit. This was really... Look how off-center this was before. My goodness. Okay. Maybe this will work better now. I look like the type of guy to like exotic fruits. I have never in my whole earthly life have heard that before, ever. That's pretty wild. I think my computer's being, oh my God, 70 degrees. Oh, wait, what? Did I design this wrong? No way. Wow, I designed this pretty incorrectly. That's pretty stupid. What was I thinking? I can't believe this. I cannot believe how cooked this is, actually. I'm excited because we've got to solve a problem. Okay, we've got to solve a problem. This is what I have. This doesn't make any sense, right? Because there's no voltage source. I miss LT Spice. I swear to God. I don't know why this, like I didn't spot this. The web has this circuit in it. And I'm like, it's kind of like the FSR is working. I have no idea why. I intended for these to be input pins, but clearly I messed up and they're like output pins. So we can add these pull-ups manually. We've got the 2 motors. 1, 2, 3, 4, 5, 6, 7, 8. That's the limit switch. There's 10 wires. Okay, so I need a 10-pin connector instead. Great. I'm running out of room here, but if I extend this, probably extend this by 2.51. I think I still have space. And this one, 2.51. I'm trying to stay focused, even though you guys are giving me such a good time with such great questions. The question of what the cable shooter attaches to right now is not relevant. The main innovation here is the actual shooting of the cable. But right now I've got a projectile with a magnet. There's all sorts of plans in the works for more advanced things. Remote control grappling hook is something that I've been working on for a long time, but that also requires a heavy amount of mechanical innovation. That's going to take a while for me to get that right, that's for sure. So that means that we only need an external pull-up for the analog sensor and not for the digital sensor. No way did you just say YOLO in year of our Lord 2025. That takes me back. Yes, that is 1, 2, 3, 4, 5, 6. That's 10.
I made sure to include some really nice wire harnessing in this design for pretty much every electrical connection in the mechanical module. Not only does this look so much better, it prevents stress concentrations at soldered joints, and I haven't had a single wire break since implementing this harnessing.
We're going to talk a little bit about what is changed in this design. So I've reoriented the battery this way, so it gets a little bit shorter in that direction. Arc controller, courtesy of PCBWay. You guys should be very familiar with that. Very cool piece of hardware by now. Pin connectors to connect the three modules together: battery, electronics, and mechanical. And I think in all in all, it looks pretty good. We've got parts for the wristband to hook in right here. I think it's going to look pretty good. What we have here is a set of washers that gets press fit into this side. And so the rope making contact with the metal should be far less friction than making contact with the plastic. So hopefully that's good. And then the very last thing is I want to do the same thing but for this side. And I've got some pretty thick steel dowel pins. Capstan equation, classic. Okay, like the difference between that capstan and that capstan is not very much, because the angle will still be 90 degrees. Kind of this corner that the rope is going to be rubbing against. And so you can see why that would cause a lot of friction. The rope is just going to go straight through there, like this.
With the CAD now done, for the most part, it was time to print and build everything.
Yeah, I'm doing colors, guys. I'm doing design. I'm making it look nice, you know? I'm doing everything that is required. Isn't it amazing? The CAD skills that are required to make a part like this. Oh my God. And it's probably not even perfect yet.
You may have noticed I showed a lot of this process live on YouTube and also talked about some other fun things too.
Bedazzled it. It was an old, like, Michigan leotard. Unitard. No. Singlet. I'm forgetting the terminology already.
So keep an eye out for the next stream.
This video and this project is sponsored, once again, at the top of the pyramid, PCBWay. PCBWay is your one-stop shop for rapid prototyping. They do CNC machining, 3D printing, and PCB manufacturing. I've gotten all three of these services from them, and they do a really great job. They have fundamentally improved the way I do my projects. This is a board that I designed that PCBWay manufactured and assembled for me. And they got all the components that I spec'd out and put it onto the board for me. What's great about doing this is that there are a lot of really cool microcontrollers out there, but I'm not a big fan of the shapes and the integrations. This ARC controller, for instance, has a AT-SAM-D21 chip, just like the QT Pi from Adafruit, but it also contains a motor driver as well as a onboard 5-volt voltage regulator. That, coupled with the curved shape of this ARC controller, makes it an ideal choice for many of my projects.
I'm going to start by assembling the electronics module. The electrical module contains a heat sink along with it to protect the motor driver from overheating.
So there we have our finished electronics module with PCBWay's ARC controller inside, and I think it looks really good. I love to have this kind of plug and play system. I die for that sort of thing. 2 male pins on one side for power and 10 female pins on the other side to connect to the mechanical module. Make sure you click the link in the description below for $5 off PCBWay's amazing services. That's 3D printing, CNC machining, and PCB manufacturing. And now, as you can see, I've got all of the parts for our mechanical module on the table here. Now, this is the hardest one to build, so I'm just gonna get right on it.
The mechanical module is easily the most difficult module to assemble. It has around 25 internal parts and takes a couple of hours to finish. Now, with both electronics and mechanical modules done, we can move on to the final module, the battery module. But first, we have to solve an issue that will change the design of the battery module. And that brings us back to the capacitor.
Very early in my engineering career, I was already aware that a capacitor could be used as the key part of a simple analog low-pass filter, which in the context of electronics means a filter that mitigates high-frequency voltage fluctuations in a circuit. And as a hobbyist, I've always been aware of the adage that you should add a capacitor to your power supplies. It can be noisy, so make sure you add a capacitor so you can filter out that noise. I've built a lot of projects with various types of power sources, and sometimes I've noticed that they only work if a small capacitor is added across the positive and negative terminals. And I thought I had a good understanding of what my projects needed when it came to filtering. But that's before I ever even thought about taking the time to think about what type of noise is present in my circuit. Sure, I can filter at high frequencies, but what am I doing? Building a radio? I don't need to worry about frequencies. I'm working with motors. But noise also has an amplitude, and that amplitude can be higher than you think. Most of my projects use DC motors. Whether they're brushed or brushless, it doesn't matter. The Rappelling project, the Web, Charlotte, and finally, when it comes to this video, the wrist-mounted cable shooter. And there's a really interesting artifact that arises when you're using DC motors that I hadn't anticipated. DC motors are not just machines that make things move. Sure, they create motion, but they also have other unintended effects that you have to take into account when engineering with them. In electrical engineering, DC motors are typically modeled as a voltage source. Now, I know what you're thinking. Why could motors be considered a voltage source? Have you ever heard of a generator or a dynamo? Those are voltage sources, and they actually work very similar to electric motors.
The voltage generated by a motor as it spins is called the back EMF, where EMF stands for electromotive force, another word for voltage. Motors generate back EMF for the same reason dynamos do. When no external voltage is applied, a motor essentially becomes a dynamo. Inside is a coil of copper wire called the armature and a permanent magnet. It doesn't really matter, but since we're using a brushed motor, we're going to say the magnet is stationary while the armature spins. Magnetic flux, the amount of magnetic field passing through a surface, changes as the armature rotates. Faraday's law states that a changing flux induces an EMF opposing the change. With a single loop, back EMF varies through the rotation. Multiple loops arranged in series level the EMF, which rises with speed. The motor also has series resistance from the long copper windings, which is why motors get hot, and inductance from the coil. As a capacitor resists instantaneous voltage changes, an inductor resists sudden current changes. As the current rises, the inductor's changing magnetic flux generates an EMF opposing the current increase. Now let's look at what powers the motor. A simple battery. Contrary to what I might like to pretend most of the time, batteries in reality aren't just constant DC voltage sources. They have an internal resistance and capacitance. So we can model our battery with ideal components as well. A small resistor in series with a DC source and a small capacitor in parallel. The motor driver acts as a switch controlled by the SAMD21 chip on the ARC controller. Switching the motor on produces damped oscillations across the battery capacitor.
The electronics ended up being a little bit more temperamental than I anticipated just because of the amount of torque that's involved here. Here we go. Look at that massive spike.
Now I could talk to you all day about how when you put a capacitor together with a resistor and an inductor, then you end up with something called an RLC circuit. The RLC circuit shares the same dynamics as a mass spring damper system from classical dynamics. Any engineer worth your salt can tell you that they follow the standard second order differential equation dynamics. These oscillations, called RLC ringing, are derived from this second order linear dynamics and are neatly modeled with some simple math, but I'm going to try to model it in words for you instead. Initially, no current flows through the inductor and no back EMF exists. As current rises, voltage develops across the resistor and back EMF builds. If battery capacitance is too small, inductor energy can feed back into the capacitor, briefly raising the voltage above safe levels. For example, a 10 millihenry motor inductor and a 22 microfarad battery capacitor with a 0.5 amp load can briefly produce about 10.7 volts, enough to damage 10 volt rated motor drivers, like the drivers I've been using. This happens in microseconds, and it does settle at nominal voltage, but even brief spikes can break drivers. The 0.5 amp load is quite intense and is certainly the culprit in this situation, and that's approximately the amount of current that generates the torque for compressing this spring. So this project is especially prone to RLC ringing. The solution is to add a large external capacitor. I've chosen one around 2200 microfarads to store the inductor's energy and prevent harmful voltage spikes. Increasing capacitance reduces voltage rise for the same current, according to C equals Q over V.
We are trying to fit a giant capacitor in a small space. That's what we're trying to do. So the leads are going to come out. I don't know why I'm gesturing towards the screen. Like you can see where my hands are in relation to the screen. But essentially like coming out this way. And obviously they're going to be attached to the wires coming out of the battery and button and power button. In hindsight, this actually kind of fits perfectly. Like I actually can't believe how well this ended up fitting. 5 millimeters. We're done with the construction lines. Come on, I'm gonna see. Somehow the construction lines returned. That looks like prime resistor real estate right there. Tolerances by feel, everybody. Tolerances by feel.
Now that the capacitor fits very snugly, we can put it all together.
Okay, so the capacitor is in there, and to prove the capacitor is in there, I have this LED, and if we place this LED into the outlet ports here, we can see it starts out a little bit dim. If we turn this on, the light comes on, and if we take the battery out, while the capacitor is theoretically still charged, we plug the LED in, and we see it still turns on even though there's no battery, because the capacitor is storing the energy. Pretty cool. It's got a pretty large time constant.
So that's the battery module with big ass capacitor.
Jones, big ass
Charge.
went on
Charge.
Lord.
That means we have these 3 modules, which we can just easily put together. I think it looks pretty nice, don't you? Then we flash the firmware, and we have our completed system. After some testing, I noticed that my new reel coupling mechanism needed some tweaks. The gear wasn't meshing well, and I heard some noises that suggested teeth were slipping. Taking what I had learned from the Charlotte project, I cut a new gear shape for this reel that would mesh perfectly with the bevel gear by iteratively rotating and cutting the shape. This fixed the problem. I also went through a few reel shapes because I found the rope wasn't winding tightly despite the tensioner that I put in this device. Adjusting the valley of the revolved shape to be more toward the center and limiting the axial width so that the rope's upper layers don't slip off seemed to help the rope not get tangled on the reel. Also, while I previously wanted to make the reel skinnier to fit as much rope as possible, I think this may cause an issue where the lower layers are harder to pull off. This also decreases the torsional effect of the friction between the reel and the axle. I increased the radius as much as I could such that I could still fit all the rope on the reel. Eventually, I ended up with something that can fire consistently. Fire. Okay. So that's 1. That's 2. That's 3. Nice. Well, almost. Damn. After years of this, I think the reel winding process here is just inherently random, so the firing performance will also be. Now, this all turned me onto some scientific papers written about winding dynamics, and I think somewhere in this area of study will be the perfect reel shape. But I've got to do some reading and calculating myself to know for sure. I think a more immediate solution will be allowing the user to access the reel for maintenance in case things get tangled up. That's nice. I can already tell that this version is special. So thanks for watching this part. Come back next time to see the full wrist-mounted version and to talk about some very important things. Stay safe, stay amazing, and I'll see you guys in the next one.